Okay. Let's start again. Doing exercises. Let's wait for people to come back.
Nobody's outside.
Okay.
It's time.
Ah, okay.
Sí, sí. Sí. Entonces, de compras en inglés. Ok, yo el correo de, yo le envío a él el correo de I sent to him el email de Diego, but the picture,
Yeah.
listo. Sí, ok, inside en English.
Small one. Yes.
Estamos tratando que vaya con un translate simultáneo. Ok, thank you.
Gracias.
Ok, ya lo conocen.
Okay. Okay, we start. Okay, now we do the exercises like this. I give you the text of the exercise, and then you have between 5 and 10 minutes to solve it. Right? You can try to solve it alone or together with your colleagues, and then we solve it together. So the idea is to apply what we have seen so far in those exercises. So we start to do it to do some engineering calculations. Okay, now let's start with the very first exercises on link budget. Now the problem is as follows. You have a satellite. You can assume a geostationary satellite. That is sending on Earth. A signal at 10 gigahertz of frequency, and we know the power density on the ground, that is minus 100 minus 113 dB with respect to 1 watt per square meter. So instead of giving you the power in watt per square meter, I'm giving you the same quantity in dB. Now the receiver on the ground work out is the minimum power of minus 19 dB with respect to 1 milliwatt. dB with respect to 1 milliwatt. The question is simple. What is they needed. Receiver antenna gain. In dB with respect to the isotropic gradient. So we just need to define what kind of antenna we need for this link to work, and in particular what is the gain, the antenna gain. Okay. To solve this, you need to apply the concept that we have seen as far as the free space link budget is concerned. So we are not, you can consider this link to be in free space. So try to solve it by yourself or together with your colleagues, and then we solve it together. This is the kind of exercises that you can expect to find for your written test. More complex than this thing, but not too much. You can use your notes, your book, obviously, because you will be able, as I said, you are authorized to use your book and your notes also as a written test. So if something in the text is not clear, please feel free to ask. Obviously, while we are here, since I'm here, if you have questions about theory, doubts, exercises, you can come and talk with me while we are waiting for you to solve the problem. I'm here at your disposal. What if you have double cascade, you can
No, yo sé que si hay una suma, una suma que tú sumas, que es la función de la ganancia también. Yo no tengo ganancia de división.
unless I explicitly talk about that.
Como lambda sí tenemos, lambda sí tenemos. Mira, dame la potencia. ¿Cuál es la potencia? Ese es la potencia. ¿Cuál es la potencia?
La tiene que estar recibiendo del papel. Esa es la potencia que incide a esa antena.
Esto ya es. Entre un satélite y la Tierra es 1600 diales. Déjense que entre un satélite con su estacionario.
En la órbita.
La órbita es 26.000 diales. Sí, yo me acuerdo que era 36. Yo creo. Entonces,
Tiene que preguntar. Tiene que preguntar. Porque, mira, por ejemplo, la parte de acá arriba, ahorita en el satélite, se ve la distancia subiendo eso, la órbita gravitacional, y acá está la antena.
Well, yes, I would like to answer but as I said, if you have any doubt or the meaning of text or interpretation of the text, okay, any hypothesis?
Lambda también tiene velocidad cero y mismo video para él.
lambda ya tenemos, te dije que ya tenemos.
No, tenemos otro.
No, tenemos lambda porque tenemos frecuencia.
I usually ask some student to come to the blackboard and solve it. But I will not do this time. Okay, so this is a typical link budget. Nothing special. Apart that units are given in dB scale, and this is pretty typical. So the equation that we want to use is the usual one: power received is equal to the transmitted power, gain of the transmitting antenna, gain of the receiving antenna.
Aquí presiona el logaritmo.
But really, someone has already calculated all those things for us because someone is already giving us the incident power. So we can use the alternate form of the link budget, where we say that the receiving power is the incident power multiplied by the effective value. If you feel more comfortable with linear units, you can convert those dB watt per square meter in watt per square meter. And to do that, you 10 to the power you invert the definition of logarithm, and this is going to be a pretty small number. And this is why, being so small, this is why we usually prefer dB units. This is a power density that is not unusual for a satellite link. 5 times 10 to the minus 12 bar per square meter. Now, what is the power that our receiver needs to be properly working? Must be greater or equal to minus 90 dBm. Again, we convert this into linear scale, so this is going to be 10 to the power minus 90 divided by 10 milliwatts. 10 to the minus 9. Since we are using bar, please be always consistent. 10 to the minus 12 bar. Don't mix up different units, otherwise you will make wrong calculation. So, now we have all the ingredients in this equation, and we can solve this equation with the unknown, that is the area, the effective area of the antenna. The effective area of the antenna must therefore be the received power that we need, minimum, divided the incident and this is not. It's not a larger effective area. 0.2 square meters. Now what is the size of the antenna? This is the effective area. Now if you use a dish, the classical dish reflectors for this kind of antennas, if you do the theory, you find out that the area of the dish is slightly bigger than this. So in this case, the effective area is very close to the geometrical area of the reflector. So you end up with an antenna that can be 0.3 or 0.4 square meters. So an object that is not too large. It is comparable with the size of the satellite dishes that you have to receive TV. But I was not asking the area, I was asking the gain. How do we calculate this? Well, we apply the universal relation that says the gain, linear gain, is the effective area divided by lambda squared times 4. And lambda, please remember that is the frequency, speed of light divided by the frequency. We are in vacuum, so this is 3 times 8, 10 to the power 8, divided 10 gigahertz, that is 10 to the power 10. So the wavelength is very small indeed. And I wish I had calculated it, but nevertheless, the linear gain of this antenna is 2,792 for a large gain. The gain in dBi will be 10 logarithm base 10 of g 4,
Sí, donde se hace la velocidad de la luz.
5. So for our system to properly work, we need an antenna whose effective area is 0.2 square meter, that at this frequency corresponds to a very high gain. Very high gain of almost 2,000 with respect to the isotopic range. Questions?
Can you repeat about the lambda value?
Lambda is the wavelength.
Yeah. So
It is defined as the ratio between the speed of light
how
and
do
the
you
frequency.
consider that? It's a general consideration.
This equation, yes, this is the definition of wavelength. Yes, it's always the speed of light divided by the frequency. It is the distance
Nunca resolvemos
that the electromagnetic wave propagates in one period. So is the velocity for the time, for the period, where t is the duration of a cycle. And this is 1 divided by f.
Those values are constant.
The speed of light, as far as we are concerned, in vacuum is constant. This will change if you propagate in a medium that is different from the for example, in water or in a wall. The frequency depends on the exercise. Depends on your application. The equation is always valid. Just as it would be the rest.
So I'm not sure what do you consider that particular value.
Because it was given the text. Was given by the signal was attended.
So if you tell us about a different media, you are going to give us the value of the constant?
I will possibly give you the dielectric constant. And then if you remember, the velocity is given by the velocity of light divided by the square root of the dielectric constant. So I usually give you this. I don't give you the dielectric velocity, I give you the dielectric constant. And then so your wavelength in that case will be C divided, that will be the wavelength. More questions? Okay. May I wipe up this?
No.
Okay, another exercise. Now we have a microwave communication link. From point A to point B over a distance of 20 kilometers. Now the transmitted power, so this is the transmitter and this is the receiver. The transmitted power is plus 20 dBm. And those antennas have an effective area of 0.2 square meters. So they are reflectors, their size, their area corresponds to 0.2 square meters of effective area. Now the system can work at 20 or 30 gigahertz. using the same antennas. So it is a dual frequency transmitter. You can switch between 20 or 30 gigahertz freely. The question is, calculate the difference in dB between the received signals at 20 and 30. That is, I want to know which one is strongest. If the signal at 20 or the signal at 30 gigahertz. Remember that we are transmitting in both cases the same power. The antennas are the same. I'm asking you if there is a difference. What is this difference in dB? And then I will tell you why we use dual frequency systems. This is another. There is the ground here, but ignore it. So there is no reflection from the ground at this time, just a direct link. So consider it as free space. So again, a link budget problem. Again, 5 minutes to solve it, and then we do it together. Is clear? Any doubt about the question? It's clear what I'm asking?
La señal entre 20 y 30.
Pero tipo lo recibe.
Aquí se recibe.
Nothing changes, and then you have the. Okay, any hypothesis? Someone has reached a conclusion? What is the difference? Don't worry. This is not an evaluation. Sorry. Okay. What changes? Okay, let's write down the lean budget equation. Transmitted power. You can always choose the most convenient form of the lean budget equation. Depends on your input data. So I choose this one.
En español, el presupuesto en el lápiz, más o menos. Es cuando tú sumas todo y le quitas las pérdidas te da un valor. Eso es lo que
As you possibly remember, this is the incident power test. I use this because I have already the effective area. And the effective area does not change when you go from one frequency to another. What changes between the two frequencies? The gain. Because the gain is effective area and if you change the wavelength, the gain will change. So, gain of the transmitter at 20 gigahertz, the wavelength at 20 gigahertz is 0.015 meters, 1.5 centimeters, very short wavelength. And if you put this number in here, you get the gain at 20, that is 1.1 10 to the power 4. The same antenna used at the higher frequency will have a higher gain because the wavelength will be smaller. Gigahertz, the wavelength is 1 centimeter. And this gives you a gain of 30. from this, everything else in this equation does not change. The transmitting power is 20 dBm, that is 0.1 watt. The distance is 20 kilometers, the effective area at the receiver does not change. So you can do the two calculations at 20 and at 30 gigahertz. And you find that the power received at 20 gigahertz, if you put in the numbers, is 4.44 10 to the minus 8 power. At 30 gigahertz, since the transmitting gain is higher, also the receiving power is higher. And obviously, if you do the ratio between those two things, it will be exactly equal to the ratio of the gain, because the difference is the gain. So if you calculate these quantities in dB with respect to 1 watt, you find that this is minus 73.5 dB watt. And this is minus 70 dB watt. Now, I'm asking you the difference in dB between the two. You can calculate this by, so in dB, it is minus this is one way to calculate it, by making the difference, or you can calculate it as the ratio of linear powers. So is it dB of dB watt? It is and you obviously get 3.5. So, for this system, the signal at 30 gigahertz is definitely stronger than the signal that you receive at 20 gigahertz using the same antennas and the same transmitting power. We are transmitting the same power and we are using the same antennas. Nevertheless, the power received at 30 gigahertz is stronger than what we receive at 20, because the free space loss. So why do we use dual frequencies? Why don't we use 30 gigahertz? Because it's stronger. And you cannot know for sure, but if you have rain along the link, the signal at 30 gigahertz is more attenuated than the signal at 20 gigahertz because of rain. So when you have heavy rain, I will not, it is outside the scope of this course, but if you have heavy rain, what happens is that the signal at 20 gigahertz becomes stronger than the signal at 30 gigahertz. So those systems work so that they usually work at higher frequencies because you have more bandwidth, your signal is more strong. When you have a heavy rain event along the limit, it switches to lower frequency and is less attenuated. Questions? Yes.
In that case, the signal of the difference is negative.
In this case,
In the second case that you told us.
oh yes, because if you have rain, then you will find that the signal at 30 is lower than the signal at 30. So the difference becomes negative.
And what is the interpretation?
Interpretation is simply that the signal at 30
It's
gigahertz
positive
is
and
stronger.
negative. In both cases, positive and negative, what is the interpretation?
If the difference is positive, it means that this is bigger than this. If it is negative, it means that this is smaller than this. It's just the way which is stronger, which is bigger. Zero means they are equal. 0 dB, a difference of 0 dB means they are equal. More questions? Okay, let's do something that is always on the budget, but with a different perspective. Okay, you have a customer, you are an engineer, so you have a customer, and your task is this. Okay, a customer comes to you and tells you, I want you to design a system with an equivalent isotropic radiated power of 1 megawatt, 1 million watt. And you have to decide which transmitter and which antenna you have to install to guarantee that value of A. Remember, I told you that during the lecture. For a given AMP, a user, if the AMP is the same, is constant, the user does not notice any change. So you can obtain this value of AMP with any combination of transmitted power and antenna gain. Please remember that A is transmitted power time and transmitted antenna gain. If this product is constant, the user does always receive the same signal. It's up to you to choose how to balance the two things. What is the criterion? The criterion is you want to have your customer spend less possible amount of money. So you have to calculate, in other words, the transmitted power and the antenna gain, minimizing the total cost for your customer. And the antenna cost is as follows. You have some models for the antenna cost. This can be, I don't know, dollars, euros, whatever you want. You can imagine those are dollars, where Ka is a constant that is equal to 10. Kd is 3 times 6. G is the linear gain of the antenna. Linear gain means not in dB. And P is the power of the transmitter in part. Now, with those cost model, you have to design the system for your customer, minimizing the total cost of the system. If you make a mistake, you have to pay the difference from your own pocket. Okay? That's what usually happens. So, the criteria is minimum cost. Enjoy. 5 minutes, 10 minutes, and then we solve it together.